Hi everyone. So I'm Stephen Jones. I am my job is to be the architect of CUDA, and so I spend a lot of my time looking at just the things that run all of the AI stuff that sits on the GPU. So I'm going to tell you a bit about how sort of I perceive the world and the kind of things that we do inside CUDA. And the first thing really to talk about is that when I think of CUDA, obviously it's known as a programming language, but it's actually an entire platform, and I'm looking at the platform as a whole. So both here on the right-hand side, from the standard language, the CUDA C++ extended language for parallel programming, all the way through other languages, libraries, frameworks, applications. The people who sit and use the GPU are intersecting with it at all these different places, right? So I'm looking at the structure of the platform as a whole, the ecosystem as a whole, to try and see what is it we can do to make things interact better, more efficiently, more optimally. So to give you an example, here's a piece of the ecosystem stack that everyone in this room is probably familiar with, where involving everything from libraries through to frameworks through to specific applications. And, you'll recognize most of the things on this. But in fact, when I sit down and I look at it from my perspective, that is one piece of the whole that CUDA is running. And so, if you look here at this picture, CUDA sits here across the width of this thing at the bottom. It sits above all the different types of hardware that you can program with it. So all the different GPUs, but also the cloud providers, the OEMs who produce machines, all of those things is what CUDA talks to. And then everything sits above it that CUDA is providing the basis for running. And so we've got the libraries, we've got the frameworks, and we've got a bunch of different application spaces, not only deep learning, but also scientific applications, dedicated consumer applications, things like Photoshop and graphics and so on. And all of these things come together in this ecosystem that I was talking about. And what's really interesting to me is the way that we can do things at the CUDA level or at the libraries level, or in fact anywhere around in this stack, and make a significant difference to how these things perform individually and how they relate to each other. And as I said, I'm going to talk to you about some of that. But one of the interesting things we did, we went away and we ran some experiments. These are some numbers gathered from a bunch of HPC applications, because they cover a really broad breadth of different, a broad gamut of different types of application. And we ran these things on CUDA 8 from 2 years ago, and CUDA 9 and CUDA 10, 2 years worth of software on the same hardware, and changes we had made to the software alone. And that's, across that stack, as I was saying, made a performance increase of 2x purely on the software side. Then you add to that another generation of hardware that came out in last year, the VOLTA hardware, and you get an additional 1.5x on that. So the way that the performance and the behavior of your applications changes is as much or even more sometimes related to the software stack as it is to the hardware generations, right? So a couple of months ago in September, we released CUDA 10. And CUDA 10, of course, we try and release a major release every year. And this is just a list of some of the things, and I'm going to drill down into a couple of these, that CUDA 10 addresses. So when we come out with just one release, we're touching on systems, we're touching on platform, we're touching on libraries, we're touching on tools, we're touching on this whole ecosystem of things, as I said. And this allows us to move all of these pieces forward at the same time. And so I'm going to give you an interesting little example of the way that things that happen at the system level can affect things across the board. So, many of you, probably everyone in this room at this point, has heard of NVIDIA's DGX-2 machine. This, the monster machine. It really is a supercomputer in a box. 2 petaflops of half-precision performance, and 16 GPUs inside. But one of the things that happened with DGX-2 is not only the bringing of all of that hardware into one place, but this thing is the heart of DGX-2. This is the NVSWITCH. This is a piece of hardware that sits in the middle of it and allows a connection between these GPUs in an amazing way. And I'll tell you a bit about this because I think it's really interesting as a motivator for how some of the system stuff I'm talking about applies as a whole, right? So the DGX-2 itself you've probably seen this breakdown, 16 V100 voltas. It's got 12 NV switches. The bisection bandwidth of this thing is 2.4 terabytes per second. That is a carrier-class rack of networking equipment sitting inside a few very small chips. And so the interconnect on this thing is absolutely incredible. And then a bunch of storage and other things. It's a really impressive box. If you look at it sort of figuratively, the way that I picture this as a software developer, I've got 16 GPUs, each with 32 gigabytes on top of each other, and a very, very fast interconnect provided by NVSWITCH in between. And in some ways, this really does look like a supercomputer. Every one of these GPUs is capable of 15 teraflops of floating point performance, a lot more if you're looking at the 16-bit floating point performance. And I've got this interconnect, which is a network running at 300 gigabytes per second, which is just astonishing, right? So the NVSWITCH network connects all of these things together so everybody can touch and see everybody else in the system. And so what we have in some ways, we've got inside one box, we have a scale-out system. We have a system which literally connects things which used to be entire racks or at least entire blades, and now it's all in one single box. And so now looking at this, we say, well, let's talk about this and see, from these disparate things, what can we do on the software side, on the system side, to change the nature of this in a way that affects everybody? And so one of the things that we did with CUDA, and we spent many years developing this, is we brought out this thing called unified memory. One of the things I'm always trying to do as we're developing our software is come up with things which transparently and easily facilitate access from software to these functionalities. So what unified memory does, for example, is it says, okay, let's take these 16 GPUs, let's take the 16 independent pieces of memory, let's recognize that what this switch is doing for me is this amazing memory level interconnect between them, and let's unify that whole memory. So now what I really have is 16 GPUs welded together with a single giant pool of data between them. I have literally turned this thing from a scale-out into a scale-up system. The density of this system behaves exactly like a GPU 16 times its size, which is a really incredible thing to do, because now I can take a piece of software and I can just drop it with no changes on this machine. And I can run it across all of this power. And I can get the speed-ups both from the bandwidth and from the simplification of the system from the software perspective. So when you run a few benchmarks on this, these particular numbers here, we are comparing here the two DGX1 systems, which is 16 GPUs worth without the switch, with a DGX2 system, which is 16 GPUs with the switch and with the system software driving it. And you can see simply by changes in the system-level architecture, a piece of software with no significant changes to it is running twice as fast or more than twice as fast. And this isn't just one piece of software, right? On the left-hand side, we've got everything from quantum chromodynamics through weather forecasting, recommender networks, and language models. All of these things can benefit from something that happens deep, deep down inside. And so these are the kind of things we're looking at when we're saying, what can we do with the CUDA platform? Right? What can we do at the system level? What can we do at the language level? What can we do at the whole ecosystem level? So I'll give you another example. Here's some of the programming model stuff which we worked on again in CUDA 10.0. Lots of different features again. We've got graphics, we've got compilers, we've got mixed precision, and one of the things which I paid a lot of attention to is the programming model, the language of it. So I'm going to tell you just a little bit about that as well to give you a taste for the kind of things we can do at the CUDA level which affects this whole stack. Right. So one of the things, or the main thing that we added to the programming model in CUDA 10, which, as I said, came out back in September, was task graphs. Task graphs is about recognizing that a program typically does the same thing over and over and over again. And so if I capture what that thing is, and you'll all be familiar with that because pretty much any deep learning or AI framework you'll describe your workflow as a graph of work. We can capture that and we can apply optimizations to it as a whole program optimization in a way that can turn on and enable a lot of interesting new things which would not be possible before. So sort of the key element of a task graph is that I can define it once and I can just launch it bam, 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 repeatedly, very, very, very rapidly. And these optimizations are then applied. And what you get from that is you say, well, I can now kick off an entire pile of work in a single step. And what that single step does for me is it says, right, well, what previously was a lot of work and effort being spent, sending that work to control the GPUs, on one of these DGX2 systems, 16 GPUs worth of work, I can now kick all of that off in a single step. And what that does is that frees up my CPU resources for me to do a bunch of other things. But it does more than that, right? It also says, well, I've optimized this workflow end to end. And so not only am I seeing, savings of 30, 50% on the CPU side, on the GPU side, execution side, I'm saving a whole bunch of time as well. We can run this, and I explicitly picked, a general purpose library like an FFT. And for small size FFTs, you can see like a 25% speed up, for example, on some of these things. And if you stop for a moment and think about it, 25% speed up, that is half of a generational GPU, right? That is half of the benefit you get from moving an entire GPU hardware generation. And that's from one software feature, right? So these are the things that I'm looking at when we say, right, what can we do for CUDA? How can we apply it to not just a language, but to all of the things sitting on top of it? So the thing that I think is really exciting to me is not only do we get to do things on this green layer at the bottom, which project upwards, but we also get to link the layers between each other. And there's some really fascinating research about that as well. And so, these application spaces which live at the top, getting them together to interact together, and obviously the really, really interesting work right now is to interact some of these, say, the scientific applications with the AI space to have this fusion drive these things, right? And so what we're getting, and we're seeing more and more in the scientific communities, just last Tuesday I was sitting down with a bunch of researchers and they were going through some of the things that they're working on, and they are finding all of these fascinating ways to combine the work they're doing. Now, these guys are writing in native CUDA or in OpenACC or a native parallel programming language, and then they're bringing in the AI space, and they're saying, let's apply this to my problem, and let's make this better. So here we have, drug discovery gets benefits. Cancer research, where you're bringing AI in to optimize by an order of magnitude the way that you search through cancer. The LIGO gravitational wave accelerator. They sped things up by a factor of about 5,000 using AI to process the signals from this thing. Nuclear fusion. They use AIs to control the fusion reactor itself, so that as it goes unstable, they can control the magnets to bring it back in stability and stop this fusion reactor exploding. It's amazing to see how these different areas of the stack that sit above CUDA start interacting together and start playing with each other and doing things that were never possible before. And really, the thing that is driving all this is something that I think we're all familiar with at this point, which is these tensor cores that live inside the GPU. So when I sit and I look at the GPU and I think, right, when we come out with hardware, what can we do with this hardware to enable these types of things to happen, right? So another thing that happened, of course, a couple of months ago was NVIDIA's release of the Turing architecture. Now, the Turing architecture brings a whole pile of new things to it. When talking tensor cores, Turing's tensor cores take what VOLTA was already doing with half-precision floating point and extends it to a range of new precisions, right? You've got, not only has it boosted the performance of the individual half-precision FP16 tensor cores, we've brought in as well int8, int4, and even single-bit binarized tensor cores for research purposes. And so, the hardware brings these new things in, and so I sit there and I say, right, what can we do with CUDA to expose this, to give access to these applications, both at the library level and even directly at the programming level. So, yet another thing we did with CUDA 10, obviously, support for the Turing architecture. We want to bring out every single one of the new hardware features that are available. And so we've got architecture, tensor cores, ray tracing. It's got all sorts of interesting things going on. I'm going to tell you a little bit about what we do with the tensor cores, because I think, obviously, particularly relevant to this audience. The tensor cores bring as a first-class component 8-bit integer matrix operations. This WMMA you see on the left is what is CUDA's name. It's the function that CUDA provides for accessing these at the programmatic level. But it's not the only thing we provide, and I'll get to that in a moment. And so the tensor cores work on matrix operations of various different aspect ratios. And so what we see in CUDA is we have, a series of different sizes and classes specifically designed for the cases where if you are a researcher and you want to be dropping in, a custom layer into your model, we've given you, and we've built for you the tools to be able to do this at all of these different precisions, right? So one of the things that I'm very excited about is something that we've built, which is a source level library called CUTLASS that sits inside the code that, say, these HPC scientists are writing to give them access to this. Not only, therefore, can you call a library to use the tensor cores, you can actually embed that code directly into the rest of your program. So you can make it a first-class component to do the inference work or whatever other things you need combined into the scientific simulations or whatever that these people are doing. And by providing with a library which sits at a higher level than just the raw language, so you can say, okay, please define your matrix operation, and we will go away and we'll make it all happen for you. So this CUTLASS library, for example, it provides 90% of the performance of the hand-tuned assembly code that the libraries use. So the NVIDIA ninjas will hit 100% on all of this. But you can just drop stuff straight into your code and get 90% of that without even trying. And that kind of thing is very exciting to me. So it's hard to talk about Turing without touching on a couple of last little pieces. And I think, yet again, these are very interesting examples of how the combination of hardware, platform software, and application-level software combined to provide some completely new things that can be done. So, Turing's hardware Turing includes hardware-accelerated ray tracing, which is very interesting and has some beautiful demos associated with it. But what we do for ray tracing is, as NVIDIA also has a platform called Optics, which is a ray tracing platform, which exists in the professional graphics world and the gaming world. And Optics allows normal CUDA C++ access, as well as its own set of framework, to provide these ray tracing functionalities. And again, what you see coming into this then is, now that I'm touching the CUDA platform with this, I can bring in AI accelerated rendering together with my hardware accelerated ray tracing, and I can start to do really fascinating things, which some of you will probably have seen through NVIDIA's research. And finally, something really worth touching on as well, and I'll wrap up with this thing, is something we call NGX. And NGX is really, really interesting to me, because NGX is a stack of software that the Quadro organization in the professional graphics organization NVIDIA develops. And on top of that stack is a whole series of things which run all the way up through the graphics drivers, the ray tracing capabilities, up to the application software. And what we can then do is NGX specifically brings AI operations into the rendering pipeline. And that lets you do amazing things that were not possible before. So Photoshop, as an example of what you can do with it, we took an upscaling inference model into Photoshop, so you can take images in Photoshop and you can dramatically improve the quality of them at extremely low cost. Another demonstration we showed was AI-driven in-painting, where you can fill in elements and components of an image and smoothly blend things, remove things, edit things. This kind of stuff is amazing, and you can just literally fire up Photoshop, and suddenly we've brought in plugins of AI together with the professional graphics that the artists are doing. So, it's just a very quick touch on the kind of things that I find really fascinating about where CUDA is right now, which is this platform that stretches all the way from hardware up to software, and the kind of things we can do to unify these, to bring them in together and touch games and professional graphics and scientific applications, all bringing together the deep learning research, which we'll be hearing a lot more about today. So thank you very much.
Okay. Can you guys hear me off? I don't use the mic. You should use recorded? Okay. I like to walk around, but okay. So I'm going to talk to you guys about cuDNN today, which is really the other half of the core platform that deep learning researchers rely on for their work. Stephen talked about the first one, which was the general CUDA programming language, and then cuDNN is the math library that accelerates the common functions needed by deep learning frameworks. And these are not the slides. Okay. This is not the deck. I'll keep talking. Yeah. So, do you want to bring my laptop? Okay. So, most of the audience are deep learning researchers, and performance is really important to you guys. The more data you have that you can train with, the more relevant and accurate results you're going to get. The faster you can iterate your training times, the more experiments you can do before that paper deadline. And so performance is critical, and that's what cuDNN is really all about, and that's kind of what runs through the blood of the engineering team working on it. And performance really, it's two things, right? Stephen had the first half, which was when you're doing something new, you're doing research, you're going to be trying different things and things that people haven't done before. You want a general programming language like CUDA that you can do things in parallel and fast, but you can write up your own new ideas and creative approaches and still get good productivity and performance. And then what cuDNN does is it gives you all the fundamental building blocks that you can also get really good performance with. And what I'm going to walk through today is a little bit about how we go about it, what it is, and give you some examples of recent performance improvements we've made along these lines. Because even within a library like cuDNN, there are many different options and use cases. Not everyone is running a ResNet type thing. And so what we've been working on a lot ever since we released VOLTA and TensorCores is improving the performance of some of those other use cases, and I'll walk you guys through that as well. And excuse me. Okay, yep, these look good, thanks. So a little bit about how we go about doing cuDNN. So we work very closely with the architecture team at NVIDIA, and you can think about it as being designed in cooperation, both the hardware and the math libraries. In fact, you can think of a really good example of this is TensorCores, based on work that we were doing in terms of trying to optimize the common kernels for deep learning. We had some ideas on how to make them go faster and worked with the hardware team to get those ideas implemented in the new architecture called TensorCores that's in VOLTA and TURING. And by nature of that, when TensorCores were ready, that support's also ready in cuDNN. And there's a healthy code design, and then now that we've just got TensorCores, we've been working on making sure we get the utmost performance out of it in all the various use cases. And then you'll see this cycle run through again, because now we're taking new ideas and they're going to put it into future generations of our hardware as well. So there's a very close cooperation there. In fact, many of the people that work on the cuDNN library are actually part of the architecture team for that very reason. The other thing I wanted to point about cuDNN is the API is very straightforward to integrate into deep learning frameworks. If you're doing systems research or you're trying to create something from scratch, your own framework to support your research, cuDNN should be very straightforward to take advantage of. And the interface and the data layouts, it's all relatively, it's all designed so that you can call these routines in a independent fashion. You don't have a lot of hidden state or anything like that that makes the library hard to use. It should be very straightforward to take advantage of. The one thing I wanted to mention, if people aren't aware, that we've changed since probably the last time the last NeurIPS conference, is that we started doing monthly releases of the cuDNN library. And this is because we wanted to get the performance improvements we've been making with TensorCores out to you guys as soon as possible. And you can get these updates either through the containers that NVIDIA publishes on NGC that have our optimized deep learning frameworks, or you can go to the cuDNN website to get them. And finally, I just wanted to mention, just as a reference, that I could have given this talk with one of maybe 7 hats on. cuDNN is one of the libraries that we work on. There's also a BLAS library and a sparse linear algebra, random number, et cetera. And we take the same approach with all of these. Okay, so I want to dive right into some of the performance improvements we've made to give you guys a flavor of what we've worked on. This is not a comprehensive list of all the performance, but it's enough to hopefully convey a sense of the type of work we're doing in the library and motivate why it's probably useful for you guys to go get the monthly updates as well. So one of the things that we've been focused very highly focused on recently is improving the heuristics that the cuDNN library uses to choose which convolution algorithm or kernel to run for your particular use case. The library actually has many, many implementations underneath the hood of how to do something like convolutions. And it uses a heuristic to decide which of those kernels to use in any specific instance. And as researchers, you guys are trying lots of different things, and we're finding that we have to constantly be improving these heuristics to capture the full breadth of what the community is doing. And one of the things we've seen actually is as people start scaling out their research and trying to run training on larger and larger data sets, larger and larger models, but also more and more machines, one of the things we're seeing is that people are running not just with sort of typically large batch sizes on each GPU, but they're running with smaller and smaller batch sizes per GPU as well. And so we wanted to make sure we improve performance across the range of these things. And so what this chart here is showing is the performance improvements from last year, the cuDNN that was released about a year ago at December last year, to what we released last month. And what's shown is there's a bar for each unique call to cuDNN convolution from, in this case, is when you're training the SSD model. And I've got it shown for 3 different cases, batch size 32 per GPU up to batch size 256. And this dark line here is the 1.0x. And so you can see that we've been finding the cases where the heuristics weren't making the optimal choice before. We actually have a really fast kernel, and now it's doing a better job of choosing the best kernel in these various scenarios. And you can see in some cases, this is a log scale, choosing the right kernel can actually give you a very large speed up for any particular convolution. Now, this doesn't mean you're going to see a 10x speed up from last year to this year training the SSD model, because what I'm not showing is how long each of these kernels are running. So you'd have to do a weighted, you'd have to weight these by that. And I'm not showing overheads from outside of the cuDNN library. But this should give you an idea that a relatively large fraction of these kernels are going much faster with the improvements we've made over the last year as we're honing in the best way to take advantage of the TensorCore performance. So that's the first thing. And SSD is just one example. We've been doing this with lots of different models and research models we've seen. So this improvement in the heuristics is actually fairly broadly applicable. And I think if you're using an older version of cuDNN and you go get a newer version, you're definitely going to see an improvement. One specific area we've made an improvement on is persistent RNNs implementations. So to give a quick background on what this is when you're evaluating a recurrent neural network, each time step you're going to be in the naive implementation storing and loading the weights for that model, and a persistent implementation, a persistent algorithm for implementing RNNs allows you to keep all those weights inside the registers or the shared memory of the GPU, so you don't have to do that and you can run faster. And so doing that while taking advantage of TensorCores was something we focused on over the last year. So to give you an example, what I'm showing here is performance for all the unique persistent RNN calls for training the Google Neural Machine Translation model. And you may be thinking, well, oh, that model has, a handful of RNN layers. Why are there so many calls here, even if you take into account forward and backward variations? It's because as you're training, this is, I think, was on, English, German data set, and based on your batch size, you're going to have different maximum sequence lengths that you're pumping through during the training, and so you'll see sort of like a little variation there. And that's as you're doing the training, you're going to have different maximum sequence lengths in your batches. So that's why there's so many different calls. But the library has been optimized for a lot of these sequence lengths. And you can see again here, this line here is the 1.0x line. And you can see for many of these calls, the persistent implementation has improved performance in many multiples. So if you're doing research, you're trying to train recurrent neural networks, and you're doing it with a batch size where you can take advantage of these persistent implementations. And for the case of this model, I think you can go up to batch size 128 on a VOLTA V100 and still take advantage of the persistent implementation. This also helps on the inference side as well. So that's another example of an area we've been optimizing. A third example is the case where you have strided convolutions. And in particular, when we did an analysis and we dug into many of these models, and pretty much every modern, most modern, I would say, image classification networks have strided convolutions, and these are also used as backbones for object detection as well. And as we dug into it, we found that the way we were using TensorCores for doing the backward activation gradient calculation for these strided convolutions had a room for optimization. And so what we did was we optimized that use case. This model I'm showing here actually is not an image model, it's deep speech 2. And I'm showing it because it's a particularly acute, it's one of the models that a particularly acute performance improvement from our optimization because of the way the few convolution layers at the start of the model before you fed into the recurrent part are specified. And what you see here is, the forward, the activation gradient calculation, and the weight gradient calculation. And you see fewer activation gradients here because there's only a small number of convolutions, and you don't have to calculate the activation gradient for the very first input coming into the model. And so you're going to have fewer activation gradient kernel calls. And again, there's only a few convolutions, but the reason you see so many columns in general is because there's different sequence lengths that you're going to be passing in as you do iteration over the training run. And in this case, you can see actually, again, it's a log scale. Oops, it's a log scale, and there's more than 10x improvement for this convolution use case on Deep Speech 2. Some of the image classification models will see a more modest improvement because they were like 3x3 convolutions with a stride of 2 or something, whereas what Deep Speech 2 had was a much more extreme case of the striding. Thank you so much. The final chart I want to show is the performance is a feature that we've added into cuDNN over the last year that lets you train FP32 models with TensorCores. So to give a little context for this, generally the recommended way to take advantage of TensorCores is to train your model with mixed precision. And we have a documentation that explains on if you're using TensorFlow or PyTorch or MXNet or various frameworks how you can train your model in mixed precision. You want the weights to be trained in floating point 16 format, so you can take maximal advantage of TensorCores. One feature we added was so that to enable people to get the advantage of TensorCores, even if you're training your model with single precision or floating point FP32, just as a very quick way to get the benefit in case you haven't converted your model to mixed precision yet. And this is something that's actually enabled through TensorFlow as an experimental feature that's available in our containers. You still need to use law scaling, but you don't have to convert your model to 16-bit floating point. And in this case, you can see, the performance improvement from last year to this year for a variety of models at different batch sizes. And basically, just by using TensorCores, you get a 1 to 2x performance improvement for relatively little changes, which is a nice way to get a speed up in TensorFlow if you haven't modified your model to be mixed precision yet. Okay. These are just, like I said, these were just a flavor. I have a few more examples. I don't have graphs for all of them, just to keep things moving. But there's some other examples here. One of the things that is important if you want to get the maximal performance out of TensorCores is, especially on convolutional models, is to have the data laid out in NHWC format, which is channel last. And in that format, you want to keep your data in that format through the entire model. One of the optimization opportunities we found was that outside the convolutions, there were other operators in people's models, pooling, various kinds of pooling, batch normalization, that we could optimize even further reading and storing data in this format, because those operations tended to be more limited by the bandwidth that how you use the memory bandwidth to load and store the data, because they weren't as computationally heavy as convolutions. So those have optimized implementations in the latest cuDNN. The other thing we did was to automatically within the library pad your input dimensions where needed to the right multiple, so you can take advantage, so you can use TensorCores for the computation, whereas previously it would have not used TensorCores if your inputs didn't quite match the dimensionality restrictions needed. And there's a memory operation required there, but it's often worth it in order to get the several x speed up you get from actually taking advantage of the TensorCore math. And the final one I want to talk about is that cuDNN now has support for the int8 TensorCores, which Stephen talked about earlier as well, that we added support for in CUDA and CUDA 10. And this is really useful for inference use cases, both data center and embedded and automotive use cases through our Turing and Xavier architectures. Okay, so we spent a lot of time on TensorCores. If you have a VOLTA V100 or using one in the cloud, you're really going to benefit from the latest cuDNN. There are some more general performance improvements we've worked on as well. Excuse me, the first one listed here, we talked about already. I showed a graph, and that applies to actually a wide variety of models that I talked about. The second thing I want to point out is we improved the performance of dilated convolutions, which are used in things like wavenets, if you're training wavenets. And then the other thing was depth-wise separable convolutions. This is something used in models like Exception, MobileNet, and those have been optimized in the latest version. We are working in the moment also on optimizing grouped convolutions. That should be up in the next future release of cuDNN. And that's great for models like ResNext, for instance. Okay, so in addition to all these performance improvements that we, spend our nights thinking about and then our days actually implementing and improving, I wanted to highlight a feature that might be useful to all of you, whether you're actually coding to the API directly or whether you're using cuDNN indirectly through a framework like TensorFlow or PyTorch. And that is that ability to log the calls made to the cuDNN APIs by the deep learning frameworks. And so this is something that can be turned on. The documentation explains how to turn it on with an environment variable. And what it does is it takes the input parameters for every API call made to cuDNN and logs it to a file that you can then use to either understand how you're using the library, or if you're doing something interesting, creative, and the performance isn't what you expect, this is a log that you can provide back to us, and we can use it to, as a guide for our own optimization. Okay, so that's basically what I'm going to cover on the recent improvements. And my last slide basically has a list of things that we're working on that you'll see in the future. Obviously, a lot more performance improvements. That every new release of cuDNN will have some kind of performance improvements. And then, since we spent so much time talking about performance, I thought I'd say a couple of words about some of the other things we're doing. One is we're planning on providing Python packaging to make it much easier to install cuDNN, improving the error messages that come out of it, as well as better support for graph compilers, which, if you're doing research into this area, if you're doing systems research, this could be helpful. And the kind of things we're doing to help support graph compilers, and just to give you an example, in case you're not familiar, graph compilers include things like XLA or TVM, if you're familiar with those. The kinds of things we're doing is making information about the scheduling and concurrency possibilities for the different kernels or the different code called by cuDNN available to the graph compiler, so we can use it in doing a better holistic schedule of a graph, and also cleaning up the way that we're specifying and allowing users to provide the algorithm choices and the various configuration options, flattening that all out so it's much more, so from a machine perspective or from a compiler perspective, it's a lot more regular. And right now it's a little bit ad hoc in how those are specified. Okay, thank you for your time. If there's one thing you take away from here is cuDNN has a lot of performance improvements in the last year for TensorCores. Go get it. Thank you.